So we kind of want to think about why are these the only three cases? And I should say the kind of quote unquote easy ways to prove these are through Q-series proofs. But what we would also be interested in, because partitions are a very combinatorial object, are combinatorial explanations. So I'm going to give what, in some maybe is a possible answer for what a combinatorial explanation of these might be. So Dyson, 1944, defines what he calls the rank. If you're given a partition, you take the largest number that appears in the sum and subtract the number of things that number of summands, and you get this number called the rank. And the reason this is called a partition statistic, and the reason we're interested in this is, well, if you go ahead and compute all the partitions of n that are congruent, and then go and kind of put them into classes based on, put them into bins based on what they are mod Q. Well, then what Dyson conjectured, and later Atkin and Swinnerton-Dyer proved, is that, well, if you do that for 5n plus 4, let's say, for example, you just compute all the partitions for 29, you go ahead and you ask, you compute all the ranks, you say, well, put them into bins based on whether or not they're 0, 1, 2, 3, or 4 mod 5. Turns out all those bins will then have the same number of partitions, which if you have 5 bins with all the same number of partitions, the total number of partitions must be divisible by 5. And this holds as well for ranks for 7n plus 5. So we're going to say this is equidistributed modulo 5 or equidistributed modulo 7, just meaning that the number congruent to 0, 1, etc. are all equal. Okay, so great. So Dyson found this really interesting combinatorial way of thinking about this congruence. Notice here that we had 3 congruences, and one of them's left out here. So what Dyson also conjectured in his paper is that there would be another statistic, which he called the crank, that would describe this congruence as well. And then in 1988, Andrews and Garvin, based on some earlier work of Garvin, defined such a statistic. So this might look a little complicated in some ways, but essentially, if you give me a partition, if there are no ones in it, then the statistic is just the largest part. If there are ones, we take the number of parts that are greater than the number of ones minus the number of ones. And it turns out this satisfies Dyson's conjecture, namely the crank is equidistributed modulo 11. And it turns out not only that, it's actually also equidistributed modulo 5 and 7 as well. Great, so in some sense, this combinatorial statistic explains all 3 of the congruences simultaneously. And that's what we'll be interested in, is doing this for K-colored partitions. So before we get to there, I'm going to just mention one way of reframing the idea of equidistribution. Namely, if we go ahead and let capital M of little m n denote the number of partitions of n with crank m, and we write down the generating function for this, which, like as Ian mentioned, there are some nice ways to write this. Namely, we have this nice product formula. It also turns out to be just eta squared over theta, if you're interested in modular forms or Jacobi forms. Well, it turns out equidistribution here is the same thing as going and starting with the else cyclotomic polynomial for a prime L and saying, let's look at the q to the ln plus beta coefficient of this 2-variable generating function. That coefficient will be a polynomial in zeta and zeta to the negative 1. And the crank being equidistributed in the way I described earlier is the same thing as just this cyclotomic polynomial dividing that coefficient. So when we go ahead and for the rest of the talk, instead of talking about equidistribution as counting the number of cranks in certain classes, we'll instead just talk about being divisible by this cyclotomic polynomial. Okay, so let's go ahead and let's talk about what the other partition congruences we want to talk about are. So first of all, I haven't told you this yet, but if you look at the partition generating function, it turns out that's just the product of 1 over 1 minus q to the n. The numbers we're going to be interested in are, well, let's just take the kth power of this product and then look at what the Q series coefficients are now. There's, of course, a combinatorial definition of this, but we're not going to be so worried about that. And it turns out you actually get a lot of congruences that look like the ones we were interested in for the partition function. So if you kind of think about, we're going to think about fixing a number of colors we're working with here. In other words, what power we're raising this all to. And we're interested in, again, these are just all the congruences, what all the Ramanujan congruences look like. So it turns out there are kind of some easy congruences first, namely if K is divisible by prime, then kind of using Freshman's dream here, you can prove that there exist a bunch of congruences by just working mod L. But what we also have are if L happens to divide K plus 1 or K plus 3, there are these two formulas right here called Euler's pentagonal number theorem and Jacobi triple product that allow us to find more congruences in certain cases. So don't worry too much if you don't know what these two things are. I'm going to state a version of Jacobi's triple product in a second, but just like Ian was talking a lot about sum to product identities, these are just two sum to product identities that are very useful. All right, so let me give an example of what these kind of congruences look like. Okay, so we start with, we have a prime L bigger than 3, and we're gonna, when 8n plus 1 is quadratic non-residue mod L, then we're gonna look at the number of colors, a number of colors is gonna be congruent to -3 mod L. In other words, that corresponds to this Jacobi's triple product we have on this previous page. It turns out that will always be divisible by L. So we're going to give kind of a sketch of the proof here. And so just to remind those who maybe know what Jacobi triple product is, or for those who don't, here's this is kind of a specialized version of what Ian gave. We specialize what the zeta is equal to. And again, don't worry too much about you don't have to worry too much about what the product and the sum actually are for right now. The important thing though is we have a product to sum formula that we're going to use. So mod L, what we're going to do to prove this theorem is you look at what's essentially the generating function for P sub K. K I'm thinking of as LT minus 3 here. We rewrite it using the definition of the generating function. If we put this 3 in the bottom, we would have just 1 minus q to the, well, now 8n, because we plugged in a q to the 8 here essentially, to the k. And we've broken this up in such a way so that in the numerator here, this product looks a lot like this product that's left-hand side of the Jacobi triple product. So we're going to replace it with this summand. It's not quite the same, only because we, instead of q to the n here, we have q to the 8, and then we also have an additional q we add in. And on the bottom, what we do, and we're going to be working mod L here, is we go ahead and use Freshman's dream to go ahead and just raise both 1 and q to the 8n to the L. And what happens here in order to actually prove this theorem is that, well, we look at what we have in the numerator now from Jacobi triple product. The only powers of q that have non-zero coefficients are those that are squares. And in the denominator, the only powers of q that have non-zero coefficients are ones that are divisible by L. So essentially, when we go ahead and multiply denominator times numerator, we have something that's square plus something divisible by L. So in other words, the only things that can be non-zero are quadratic residues. So then when we look over here and we said, well, we were assuming 8n plus 1 was a non-residue, that means this has to be 0 mod L, just because we use this congruence. So the reason I'm wanting to go through this is because this is how a lot of these proofs work. You go and you split this in a clever way, so you have a product on top that then you use a product to sum formula, like Jacobi triple product. And the denominator you want to be supported only on powers of L, or sorry, the q to the n being divisible by L. All right, so as I kind of just referenced, we have these K-colored partition congruences I just went through. And these, for lack of a better term, I'll kind of say these are easy colored partition congruences. These use these fairly common formulas in Q series. But what we also have are a bunch of other congruences where they come from is essentially if you take eta to the fourth, sixth, eighth, 10th, etc., those end up being the powers of eta that are CM forms. And so just looking at properties of coefficients of CM forms, you can prove that more congruences exist. The key difference I want to draw between these, especially these two examples, and down here though, is here we're using these product to sum formulas that are so useful, whereas here we're just using properties of the modular forms. What we're going to do is we're going to end up going and tying these back to the sum to product formulas that Ian was talking about, these McDonald identities, and we'll see how that gives us these new cranks. Okay, so let me first though quick talk about kind of a bit of history about are there ranks and cranks for k-colored partitions. Seems natural if we have them for the partition function, we should maybe have them for k-colored partitions. So in the just for two color partitions, Hammond and Lewis define a birank. I believe Andrews also defines kind of a version of this, at least in particular cases. And then Garvin extends both this birank and then also talks about rank for some of these congruences when k+1 and k+3 are divisible by L. And again, the key thing in his work is that Euler's pentagonal number theorem and Jacobi triple product, these sum to product formulas, are really what he uses to find these. But then in all these other cases I've just mentioned where we do have congruences, we at least, my co-authors and I couldn't find any type of rank or crank to explain them. So what we're going to do is we're going to use these McDonald identities that Ian was talking about. So what they are, in case you weren't at Ian's talk, I'm just going to put up the theorem that Gritsenko, Skrupa, and Zage proved. We have a product of theta functions and then a sum involving root systems. Again, it's not too important what the specific details are for us right here, right now, other than we have a sum to product formula. And just like Ian did in his talk, we can very explicitly, if we know what root system to use, we can very explicitly compute what these sums are, which in analogy with that Jacobi triple product example I gave above, we'll be able to determine divisibility of certain coefficients using the fact that we can just explicitly compute out what the coefficients are. All right, so one thing I'll quick draw your eye to as well before I go on this last slide, I had -26. There's a congruence there, but we're not going to talk about McDonald identity there because, as Ian mentioned, that's actually still an open conjecture. So while we think our crank could explain those, unfortunately, we don't know what the identity is there to use, or it hasn't been proven. Okay. So our idea here, and again, this for those of you who were at Ian's talk, he's already kind of written down this formula. We're going to take certain products of the crank generating function in order to obtain these congruences. Essentially what we want is we want to choose the right number of cranks with just a z equals 0 or zeta equals 1 plugged in, which this is just the partition generating function, as Ian mentioned, and then a certain number of crank generating functions where we have some multiple of z. In other words, you're thinking of this as just you're choosing the right powers of zeta. And the reason we want this form is so that we're going to go ahead and choose certain theta blocks to multiply by. We're going to multiply in the numerator and denominator. We're just multiplying by 1. And what we want is the numerator. We want there to be cancellation so that the only thing that's there is this theta block phi sub r. And then just like in the Jacobi triple product proof that we did above, we're going to use the sum formula coming from the theta blocks theorem I just had on the last slide, explicitly compute it and determine which coefficients are 0 mod our cyclotomic polynomial. And the denominator, and Ian was kind of showing some explicit examples at the end of this, we can go ahead and by choosing the right a sub I, or in other words, the right powers of zeta, we'll be able to group terms in a way so that the denominator is only supported on powers of q that are divisible by L. So again, this is very much an analogy with that proof we did before. The numerator has coefficients that are vanishing that we want, and then the denominator is only supported on powers of q that are divisible by L. Combining the two, we know vanishing of certain powers mod L. And essentially what this grouping of terms looks like is, well, we essentially just want to, we use the fact that 1 minus q to n times 1 minus zeta q to n, 1 minus zeta squared q to n, etc., up to L minus 1 is only supported on these powers. So essentially our whole goal is to kind of play this game where we choose the right a sub I to get our denominator to look like this, and then we're done. Okay, so just a reminder, here's what the crank generating function looks like that we're interested in. Also, sorry, I didn't really mention, but I'm saying for k odd, k even, it's basically the same thing. I'm just writing k odd to make this a little simpler notation. And so what we want to ask here is which congruences can we explain using this type of form? And it turns out that if there's not a congruence coming from L dividing k plus 14, then we're going to define our crank generating function as, well, we just choose the a sub I of k, k minus 2, k minus 4, down to 1. And if there is a congruence, we'll instead replace this k by a k plus 2, and then do k minus 2, k minus 4, etc. And so in other words, you should think of this as two crank generating functions. And we kind of just choose based on the existence of a certain congruence, which one we want to use. And the nice thing about the first definition is, as long as we don't have a crank or a congruence for k congruent to negative 14, this actually explains all possible congruences. Where on the other hand, this other family down here explains all the congruences except for when k is congruent to minus 8. So maybe in some sense this is kind of analogous to ranks, where it explains all but one of the congruences. Okay, so just to quick, give one explanation of how one could extend this a bit further. While we're saying our congruent, we have these two families that explain most of the congruences we're interested in. What I'm really getting at is we have these two families that unfortunately they can't simultaneously explain when a number is congruent to negative 8 and negative 14 mod certain primes. So let's go, but that doesn't mean that we can't ever explain those simultaneously. It just means they don't fit into either of our two families. So just to give an example, if we have 3 is congruent to negative 8 mod 11, and 3 is also congruent to negative 14 mod 17, 11 and 17 have the right properties that there will be a congruence for both of these. So what that means is the two families we introduced on the last slide, this one can't explain this congruence for 17, and this one can't explain this congruence for 8. So we might be feeling like it's a little helpless now. We can't explain all the congruences simultaneously. But it turns out that choosing a different choice of a sub I, in other words, one that's not in either of those families we mentioned, there are ways to do so. So the key thing is, in our paper, we just never really found a way to uniform family to do so for all k. All right. And so again, just a reminder, these choice of a sub I I'm referencing is we're kind of just playing this game of trying to get the right powers of zeta so that we have divisibility. All right, so just quick finish up. We have a couple of things we think would naturally extend our work. One is if we prove this McDonald identity I was referencing earlier, and Ian mentioned in his talk, we believe our cranks would explain these kind of congruences. Again, as I alluded to the last slide, we've never found this uniform choice of a sub I to explain these two congruences in particular, so that'd be really interesting to find. There are lots of examples of different types of combinatorial objects with congruences that maybe we could use theta blocks for, or something similar like these McDonald identities. And then finally, the last thing I'll mention is that I talked about kind of these easy congruences and then the hard congruences. And in this paper, Boylan's, he goes and mentions both these and says that the easy ones, I believe he calls like normal or something. Sorry, I'm getting that wrong. But then he calls the hard ones that we talked about exceptional congruences. He also classifies for k less than or equal to, I believe it's 47 odd. He finds all the congruences that could exist for k-colored partition functions. And he finds that there are just a couple that don't fit into either of those frameworks, either the easy or the hard congruences. So it'd be interesting to find cranks for those few that don't fit into these frameworks. All right. Thank you, everyone.
All right. Thank you for a fascinating talk. Are there any questions?
Yeah, I have one, if I may ask.
Yeah, please.
Yeah, so could you please go back to the slide where you explain the equidistribution with the polynomial, the divisor of.
Yeah, so you mean this one?
Yes, yes. So I'm just wondering that, I mean, the equidistribution can be seen as the exponential sum, right, by Wiener-Schoenberg theorem, or for a general measure, and for Lebesgue measure by Weil criterion.
Mm.
And so now you have, I mean, in this case, this criterion. So I was wondering, is it possible to see that in terms of exponential sum? So why I'm asking is basically, is there an effective version of this equidistribution results? I mean, has anyone computed the rate of convergence?
Not to my knowledge. Not sure though. I'm not sure if I would know the answer to that though. But yeah, that's definitely a good question though.
So yeah. So
yeah.
Is there anywhere, I mean, written this thing in terms of exponential sums?
Again, there definitely might be. I'm not aware of it. Maybe if someone else might have a better idea who's on here. Sorry, I don't think I've seen that though.
No problem. Thanks a lot. Thanks for the nice talk.
Thank you. Yeah, thank you for a good question. Sorry, I couldn't answer more.
Any other questions or comments? Okay, so if not, let's virtually thank the speaker again. Okay, great. So thanks to all of the speakers. So this, here, let me start my video. So this concludes the scientific program for today. So thanks for your participation. If you're interested, so just to remind you, we are doing board games tonight. We're playing Among Us at 7, and then Codenames at 8. There's more information on Discord, and you would be very welcome to join us. Otherwise, we reconvene tomorrow at 9 a.m. And Lucille Devon is going to give the first talk of the morning. Okay, so thank you very much, and see you either this evening or tomorrow.
Right. Bye, everyone. See you soon.